I'm delighted to be here today to talk about the big things that are shaping our future, such as artificial intelligence. Specifically, I want to talk about machine learning, a subdiscipline of AI that's now so important it's virtually synonymous with AI. Machine learning has taken our world by storm. That's astonishing to me because machine learning, for all of its remarkable success, really does only one simple thing. All it does is to discover correlations between the input for a task that you want to solve and then the desired output for that task. Let me unpack all of that by recounting one of my favorite success stories of machine learning. Every scientific field is known by its grand challenge problems. One of the grand challenges for AI has been the problem of building a translating telephone. Like the legendary Babelfish, it translates between languages in real time, enabling a smooth, uninterrupted conversation between people speaking different languages. For decades, many AI researchers, including some of my closest colleagues, have attempted this problem. They built machine translation systems in the only way that they could conceive of. They figured there had to be an interlingua that captures the meaning of statements in a source language, let's say English, so that it can be faithfully translated to a target language, let's say Mandarin. The interlingua is the stepping stone on the path between translating between languages. To traverse this path, the researchers wrote computer programs to implement a very complex pipeline of natural language tasks. These pipelines were based on the best theories about the nature of languages that linguists had come up with over 6 centuries of work. Despite many efforts, no one succeeded in building a successful translator. One of the main problems was ambiguity, which affects every step of that pipeline. The problem is that even a simple sentence can be interpreted in lots of different ways. For example, the classic sentence in this case is "time flies like an arrow," which we recognize as an idiom, meaning that time goes by very quickly. The problem is that taken literally by a machine translation system, the sentence is at least 4 ways ambiguous. It might mean, for example, I'm giving you a command right now. I want you to take out your watches and time flies in the same way you would time arrows. Or there's a special kind of fly in the world called a time fly, and it likes arrows. So these interpretations are ridiculous to us, but the only way that a traditional machine translator can avoid falling into these interpretations is if the correct interpretation is hardwired in, and that becomes unscalable. In the end, no one succeeded in building a machine translation system using traditional methods. Then the machine learning revolution swept in and solved the problem virtually overnight. It used a completely different approach based on data rather than knowledge of linguistics. Now we have 2 real-time translators that fit in your ear like a Babelfish, and they sell for under $500. Machine learning dispenses with the pipeline, and it automatically discovers correlations between words and phrases in the source language and their equivalents in the target language. It's called an end-to-end learner because it skips all the intermediate steps that people feel are essential for people to solve the task. But this is a new approach of machine learning. It depends on having a lot of data. The data in this case was cleverly speeches at the United Nations and their translation into other languages. From this data, machine learning discovered correlations in the data between the words and phrases in one language and their equivalents in other languages. This is not a simple task because each word, as we've showed earlier, means different things in different contexts. So machine learning had to discover all those subtle correlations. But machine learning succeeded because given enough data, machine learning is good at discovering obscure correlations between languages. The result was summed up nicely by Frederick Jelinek, a prominent researcher at the time, who famously said, "Every time I fire a linguist, the performance of my speech recognizer goes up." This became the rallying cry for machine learning as it succeeded in one task after another. The track record for machine learning is really quite amazing. Here are some of the machine learning success stories from just the past several years. Many of these made headlines, often by outperforming the best human experts. From my experience at SparkCognition, I know that from every one of these success stories that made the news, there's hundreds or thousands, perhaps, of others that solved a real problem but were not publicized. For machine learning, this is a truly impressive accomplishment for such a simple family of algorithms. I say machine learning is simple because it learns only one thing: correlations. Let me open the hood on this a little bit to explain what I mean. Here's a clip from a very nice tutorial on neural networks. It shows a simple application of machine learning to recognize handwritten digits, 0 through 9. By the way, this is the same technology the US Post Office uses to read zip codes on envelopes and route packages to the routing system. For this task, the input, stick with me here. For this task, the input is a digit like this 9. The task is hard because the digits are handwritten, so the same digit can be drawn in many different ways. We want a recognizer that is not confused, for example, by the curly tail on this 9. The input to this neural net is going to be a 28 by 28 array of pixels, each with a value, a so-called activation, between 0 and 1. The two-dimensional array of pixels is flattened into a sequence of 784 nodes in the neural net. The leftmost column of nodes forms the input to the neural net, and the rightmost column lists the possible outputs for the network, in this case the digits 0 to 9. And the middle layers, the middle columns, are called hidden layers, and because there's at least 2 of them, this is called a deep neural net. You may have read about them in the news. Each node passes its activation to all the other nodes to its right across the lines that connect them. It's not shown here, but importantly, remember this, each of those little lines carries a numeric weight between -1 and 1 that's applied to the activations that pass over the line. A handwritten digit is identified by propagating the activation of the input pixels through those connections, applying those weights layer by layer, so that at the end, when the activation reaches the rightmost column, the node that accumulates the greatest activation determines the network's output. In the first instance, it was a 7, and in the second, a 2. What machine learning does is to discover the weights for the connections in the network so that each input activates the right output. In this way, machine learning discovers the correlations between inputs and outputs, and that's all that it does. But the framework is very general. Our simple example used handwritten digits as input and 0 through 9 as output. It could have just as well have been English phrases as input and Mandarin as output, or any of the input-output pairs for those success stories that I showed a minute ago. I don't know about you, but I'm amazed that machine learning has solved so many hard, important problems, often outperforming the best human experts, using only knowledge of correlations. In school, in fact in life, we've all learned many types of knowledge that we draw upon to solve routine problems and hard problems. I know this from years of experience building knowledge bases like the one on the slide to support automated reasoning and question answering by computer. My work is focused on domains of science, and we coded domain knowledge in ways that enabled computers to reason with the knowledge base. Here are some of the common types of knowledge that people use, that computers use. Taxonomic knowledge places concepts in hierarchies, which enables it to inherit information from more general concepts. Partonomic knowledge describes part-whole relationships, and so on and so on and so on. Knowledge of correlations is just a sliver of human knowledge. It's arguably one of the weakest. Machine learning does pay a price for its limitation of using only correlational knowledge. In particular, it's not good for tasks that require an explanation of the system's output. If your doctor diagnoses a condition that requires surgery, you expect her to explain how she reached that conclusion. A good explanation describes the steps in the reasoning process, probably including causal inferences, spatial reasoning, counterfactuals, Machine learning skips all that stuff, focusing entirely on correlations between the input and the output of some task. Correlations make for weak explanations, and that's especially true in the case of machine-learned correlations because they're often inscrutable. But rather than complain that machine learning doesn't do everything, let's focus on exploiting what it does do. What more can we do with a tool that provides a superhuman ability to detect correlations? Current applications of machine learning are successful even when data are noisy and the signal's weak because we start with data that we believe is relevant to the task. For example, the task of recommending a book to buy might be the data about what the reader has bought recently. That information is directly relevant to the task at hand. Now, I would like to propose a new class of applications that discover actionable insight by combining signals from many sources, even ones that are only remotely connected to the task. Since machine learning is great at detecting subtle correlations, let's see if we can use it like a telescope to see things that are small and distant and the signal's weak. For example, consider the task of predicting demand for new cars in Central Texas in 2020. What sources of information might contribute to your prediction? Historical data about car sales is directly relevant, and machine learning will undoubtedly find useful trends in that data. But there are many other sources of data that might help as well, even though they're at best only indirectly relevant to the task. These might include economic data, transportation data, voting data, gasoline sales, social media. This approach of combining weak signals from a variety of indirect sources is motivated by a hunch that for many things we'd like to predict, weak signals are all around us. I'd like to describe 3 case studies conducted by my students at UT Austin that test that hunch. When the students came in and proposed these topics to me, I thought they would all surely fail, and I was wrong. Ashvin Govil's honors thesis measured public sentiment around electoral politics in social media. For many months, Ashvin applied machine learning to the social media platform Reddit, measuring support for Clinton or Trump, and he calibrated that signal against traditional polls. Then one day in October 2016, Ashvin came in my office and he predicted Trump would win. He showed me the shift in public sentiment around the time of Pizzagate and the Comey letter. The shift was slight, but it was measurable and it was telling. He found that the Reddit signal foreshadowed the polls very accurately. He could use it to assess public sentiment in real time, avoiding the 2-week delay in traditional polling. This study is one example confirming the hunch that machine learning can detect weak signals from distant sources to provide actionable insight. Now, if you find that study surprising, brace yourself for this one. Jaideep Singh's honors thesis used machine learning to search for correlations between, get this, the emotional aspect of songs played on radio stations in Saudi Arabia and major societal events there. The data were 6.8 million songs and played over 6 years, plus the lyrics for every song. We used an NLP resource called Emolex to measure the emotional content of each song's lyrics on 8 dimensions, such as anger, anticipation, joy, sadness. We considered 6 societal events, including the coronation of King Salman, the anti-corruption purge, the introduction of a new VAT tax. Incredibly, we found correlations between emotions expressed in songs played on the radios and some of these events, using the most conservative criteria for judging statistical significance. The analysis looked for a shift in emotional content of songs from a period of 2 weeks before an event to 2 weeks after the event. The correlations were across 4 events and 6 emotions. Next, Jaideep looked for a correlation between the song data and economic trends in Saudi Arabia, as measured by the Consumer Confidence Index CCI. CCI is usually measured by surveying 5,000 households, so it's not an easy piece of data to get your hands on. To my amazement, machine learning detected a correlation between the song data and the CCI. It found that the level of sadness in songs foreshadowed CCI with a lead time of 48 to 60 days. These studies provide evidence that machine learning can detect weak signals from distant sources to provide actionable insight. In fact, you could make serious money by accurately predicting an election or trends in consumer confidence. So that's my story. I hope that you'll take away 3 key points from this. First, machine learning is an incredibly powerful sensor to detect correlations, and that's all that it does. But if you're able to frame your problems in terms of correlation detection, as the clever researchers who solved machine translation did, the results can be superhuman. Coming next, I believe, is using this powerful sensor to detect faint signals from distant sources to give even more astounding results. Thank you very much.